Hello and welcome. In this problem, a water in a tank has to be brought up from a 5 degrees Celsius temperature, that is 10 kg of water, to 20 degrees Celsius by pouring some sand represented by this block, which is at 90 degrees Celsius. We want to find the amount of water, we want to find the amount of sand that must be poured, and also you can figure out what is the entropy generated because of this, because of the thermal friction that goes on because of the internal heat transfer. Okay. We have to use the SL model, and note that the pressure is not supplied, but we do know that entropy of liquid or solid when using SL model doesn't depend on pressure at all. So pressure doesn't really appear in the picture, except if you assume the pressure never changes anywhere. It's an open tank. Also, there is no heat transfer, so the tank is insulated. That's assumed ahead of time. Okay, so let's go and launch the suitable app. TESTapp, we follow the closed process branch, a generic branch, and it's assumed that you already understand how to solve problem for simple processes with uniform system. So this is a non-mixing process, obviously, because water and sand do not mix. And finally, the model to pick, it's SL model means it will allow us to use solid and liquid with the same model. So we don't have to go for the multi-model. Okay. So now let's get started. For state 1, we have liquid water. So let's leave pressure alone at 5 degrees Celsius, solid in degrees Celsius, that's good. And we have 10 kg of water. So the energy, notice that even though we don't know pressure, we have figured out what is energy of the specific energy and specific entropy of water, because it's only a function of temperature. When the water temperature rises to 20 degrees Celsius, is the same mass, state is evaluated. And now let's use state 3 for sand. Let's see, sand is available right there. And the sand temperature at T3 is 90 degrees Celsius. That's given to us. And we do not know the mass, so that's all the information we know about sand. At state 4, the sand temperature is going to be same as T3, T2, the final water temperature. And of course, sand mass is not going to change, M3. However, when you calculate, it'll be in the white background because we don't know what M3 is yet. That's one of the unknowns you want to evaluate. So you go to the process panel now that we found all the 4 states, and this is where you've got to be careful to pick all the states when you set up the process. So this is for this process. Look, the composite state, the beginning state has state 1, which is water, and state 2, which will be our sand. So we make sure, state 3, which will be sand. So that's the correctly picked state, these are the subsystems, BA and BB. In the final state, we have the subsystems again, water going from state 1 to state 2. So this has to be correspondent. And sand going from state 3 to state 4. So the picture kind of helped to set it up. So as you can see, if you go back to the PowerPoint, we have system A and B, whichever you want to call A. I think I call A as water in the app. But you get the picture. The entire system goes from B state to F state, where A and B are 2 subsystems. Yes, I call. Okay, so now that, and they're not mixing, the wall is a solid wall. So as you can see, the water remains water, sand remains sand. And we also know there is no boundary work because volume do not change. And assuming water doesn't boil, of course, water remains liquid water. And Q1, and at 90 degrees Celsius anyway, water will not boil. and Q1 equals 0 because there is no heat transfer with the external world. Now if I do a calculate, look, the energy equation gets solved. Q and W are 0. There is no external work, there is no heat transfer. And now each of these, the final mass, you will find that over here only two unknowns, but on top of that, the mass equation provides another equation. So this mass and energy equation can be solved to produce the energy of state 3. So if you go back to state 3, we should be able to find actually the unknown mass. We already knew the energy, the unknown mass has been found. M3 is 11.2. And if you come back to the process panel, notice that the entropy generation is also found. Of course, you could click super calculate to make sure all the calculations are updated. And as you can see, entropy is generated because of heat transfer. Right here it's given internal heat transfer, and the mass that must be added is shown here. Notice that this can be found even though we don't know the pressure in this problem.